video will be about terminology. That is something that is really important in order for everyone to be on the same page and understanding what is going on. And the first ODE that we're going to be solving. So let's first look at words. Words to express what we want. We're going to have quite some words that we're interested in. First, we're going to talk about the order of an ODE. The order of an ODE is the number of the highest derivative in your equation. So if you have y to the n, and n is the highest derivative that you have, here y can be a function of x, a function of t, it doesn't matter, but as long as you're taking derivatives with respect to the only variable, that is a clear enough notation. You can put the number between parentheses without having to put a lot of primes there. So if y to the nth derivative of y, that is the highest derivative that appears in your ODE, then you say that this equation is of order n. That means that y prime equals to 0 is an equation, an ODE of first order. Then there is linear versus nonlinear. As you know from algebraic equations, things like ax plus b equal to 0, this is a linear equation. And ax squared plus b equals to 0 is nonlinear. It's much easier to solve linear equations than nonlinear, and it's the same in ODEs, except that we're talking no more about just sums being linear and products of unknowns being nonlinear, but we're also talking about derivatives. Derivatives are linear operators. So if you're taking high-order derivatives, they are linear. So if you have something like y second plus y prime equals to 0, this is linear. While if you have a product of the unknown with itself, or derivatives of the unknowns multiplied by themselves, that is nonlinear. So if you have y second plus y prime times y equals to 0, this is nonlinear. Then there is a difference between constant and non-constant coefficients. This is fairly straightforward. So if you have a y second plus b y prime equal to 0, well, a and b are your coefficients, and in this case they're just values. They're constant coefficients. Well, if you look at a that depends on x, y second plus b that depends on x, y prime equal to 0, those coefficients are not constant because they depend on x themselves. Here I'm looking at y being a function of x. Trivial versus non-trivial solutions. This is the idea that a lot of complicated looking ODEs might have some very simple solutions. So for example, if you look at the equation I just wrote, well, y equal to 0 trivially solves it. Trivially because you don't have to check your computations at all. If y is equal to 0, then all its derivatives are 0, and this solves it. So the trivial solution is y of x equal to 0 everywhere. To say that it's equal to 0 everywhere, we sometimes put a third bar on the equal sign. This really means that doesn't matter the value of x at all, everywhere y is equal to 0. And this is the trivial solution. Non-trivial means that, well, there are some values of x for which this is different than 0. that is, for example, in the previous equations, we could find solutions that are non-trivial, and that might be zero at some places, but not everywhere. The difference between homogeneous and non-homogeneous is again a difference that comes from algebra. Homogeneous means that there is no constant term. Non-homogeneous means that there is a non-zero constant term. Here, constant is a little different than from algebra, because constant just means not multiplied by the solution. So I'll just rephrase it by saying homogeneous is where there is no coefficient by itself, and non-homogeneous means that there is a coefficient by itself. So homogeneous would be something like a y prime plus b y equals to 0. Non-homogeneous would be a y prime plus by equals to c. C could be itself a non-constant coefficient, so it could be depending on x itself, but it's not multiplied by y in any way or form. That's why it's non-homogeneous. The last terminology we're going to be looking at is at boundary conditions or initial conditions. Here we have to think about the fact that all the things we know in ODEs are about derivatives of the function. When we're taking derivatives, we're losing a constant. If y is equal to something something plus 3 or plus 4, when you're taking the derivative, that gets lost. So when you're solving an ODE on its own, you'll have infinitely many solutions. Think of, let's say, y prime is equal to 3. This is a fairly easy to solve. It means that y of x is equal to 3x plus or minus any value you can think of. So we're going to put it a plus k for constant for any value of k in R, any real value of k would fit in y and would solve our ODE. In order to avoid that, we have to say something about one moment in time for y. So we can say that y at 0 had a value that we know about. Y at 0 might be 5. That fixes our constant k, and then we have only one unique solution. This is an initial condition because we assume x to start at 0 and go on. We can also have boundary conditions. That means information about y between 2 points. So for example, I might know that, well, y at 1 is equal to, for example, 2 times y at 0. This would turn into an information about k as well. You can do the algebra to figure it out. While the first one is an initial condition, the second one is a boundary condition, because we assume the information that we want to be bounded between 1 and 0. Those are the intervals that we're interested in. So now that we have some terminology available to us, let's look at the first ODE. Let's look at solving the simplest case scenario. So what could be the simplest case scenario? Well, we're just gonna cherry pick for everything that we have looked at and just make the simplest option ever. So let's first think about what is the order we want to go into. Well, the first thing that is not 0. So we're going to set the order. I don't know why my computer is having troubles today. We're going to set the order equal to 1. That means that 1 is the highest derivative that we're taking. we're going to be looking at y prime and some conditions on it. Looking back, what are the other elements that we need? We need linear versus nonlinear. Definitely we're going to take linear. Constant versus non-constant coefficients. We're going to take constant coefficients. So let me write it down. We want it to be linear. So no multiplication of the solution or its derivative by itself. We want constant coefficients. And what else do we want? Well, we would like a non-trivial solution, but also, well, we'll start by a homogeneous equation. So something that has no additional term. So we have something of order 1. That means that the highest derivative that can appear is y prime. That is linear, so y prime is not multiplied by y prime nor by y. That has constant coefficients, and that is homogeneous. So what we have is that a y prime plus b y equals to 0 because we want it to be homogeneous. So this is the simplest situation that we can look at for an ODE. What are the different things we can do? Well, first we can solve the trivial case, a equal to 0. So there is no first term, we have by equal to 0. Well, it doesn't matter b at all. What we have is that y is equal to 0. Then, to simplify things, we're going to say that we divide that. So this is the first case. The second case then is a different than 0. Then we can divide everything by a, and we have y prime plus b divided by a, y equals to 0. But we know how to solve something that looks like z prime equals to c, but we're not there yet. So what we would like to go from here to there is, well, we're going to divide everything by y. So we have y prime divided by y, and then we're going to shift this term on the other side, being equal to minus b over a. And we're saying that we're going to call y prime divided by y, we say that this is z prime. How does that work? It does. We just have to be careful in when we want to go back, what is going to happen. So we have defined z to be such that z prime equal y prime divided by y. Then what is the relationship between z and y? Well, it turns out to be a fairly easy relationship. If you do the calculations, you will notice that z is equal to log y. Or equivalently, y equals to the ez. How do we figure this out? Well, we can just look at taking the derivative of z equal log of y. So what we have here is that z is a function of x. So the derivative of z is easily z prime. Y is also a function of x, and the derivative of log of y of x, all of this prime, is equal to y prime over x of x times the derivative of the logarithm, that is 1 over y. So we can do this change because we know the solution it has. And once we have this, well, z prime equals minus b over a, we have the solution of z, because we know that z of x is equal to minus b over a times x, plus possibly a constant. And now we also know how y relates to z. So this solves for y because we can solve as y of x equals exponential of z of x, and that is exponential of minus b over a x plus c. Now this, well, by distributivity of the exponential, what we can also write is times e at the c instead of plus c in the exponent. And c can take any value, so we can change this as a multiplication by a new constant, a constant a. You might wonder, well, that c can take any value in the real numbers, but the exponent of c would always be a positive value. That is true, but we have hidden something on the fact that we have taken the logarithm of y, while we don't know if y is always positive or always negative. So because of this slip in notation, we are able to just replace exponent of c with a and allow a to also take negative terms, negative values.